So picking back up on our last example, if g of x equals f of 3x minus 5, we're going to take the derivative using chain rule. So we're going to say f prime, leave the inside function alone, multiply by the derivative of the inside, which will just be 3. We're going to substitute in negative 1. So we'll have f prime of 3 times negative 1 minus 5 times 3, which will give me f prime of negative 8 times 3. Even though I don't know the value of f prime of negative 8, I do know the sign of f prime of negative 8. So I have 3 times a negative number, which will be negative. That tells me that g prime of negative 1 is in fact negative for this example. Okay? I'd like to show you a different application of the first derivative test. And so now let's look at a position function. And let's say we have a particle moving along a single line. The first question says, find the velocity of the particle at any time t is greater than or equal to 0. So we know that velocity is the derivative of position. So we're going to take the derivative and get 2t minus 7. In 4b, I want to identify any time intervals in which the particle is moving in a positive direction. So what we're going to do is we're going to take this velocity and we're going to set it equal to 0. I'll get 2t is equal to 7, or t is equal to 7 halves. We're going to make a number line, but I want to note that we can't have negative times here, so let's actually make our number line start at 0 and go on forever. And let's put 7 halves right here. Let's also label our number line as v of t, okay? So I want to pick a number in between 0 and 7 halves and a number bigger than 7 halves. And what we want to do is we want to plug it in to our velocity function, like a number like 1. 2 times 1 would be 2. 2 minus 7 would give me a negative value. A number bigger than 7 halves, say something like 4. 2 times 4 would be 8. 8 minus 7 would give me a positive value. So what this tells me is this actually tells me that s of t is going to have its position decreasing and then its position increasing, which actually tells you when the particle is moving in the positive direction. So to answer our question, the particle is moving in the positive direction, because velocity has direction, on the interval from 7 halves to infinity. Because it says justify, because v of t is positive. Then it says identify the time period where the particle is moving in the negative direction. So similarly, we're going to say the particle is moving in the negative direction on the interval from 0 to 7 halves, because v of t is negative at that point. So if it goes and starts out in the negative direction and then changes in the positive direction, it's going to change direction at t equals 7 halves, since v of t changes from negative to positive. So we're going to continue on and talk about something called the fun chart. The fun chart looks like this. F, concave up, concave down, increasing, decreasing, f prime, increasing, decreasing, positive, negative, f double prime, positive, negative. We call it the fun chart because this right here kind of looks like the word fun, although I'm not quite certain that you're going to think it's fun. So this brings us to some more information. The graph of f is going to be concave upward on an interval I if f prime is increasing on the interval. When I say concave up, we're talking about concave up like a cup. And there's my little coffee cup. Okay? The graph of f is said to be concave down on an interval if f prime is decreasing. And so I'll draw a nice concave down graph, concave down like a frown. And you'll notice that we can see some of this test for concavity information here. I can see concave up, f prime is increasing. And similarly, concave down, f prime is decreasing. Similarly, we can now also include the second derivative. If the second derivative is positive, then the graph of f is concave up. If the second derivative is negative, then the graph of f is concave down. And so I can see that also in my chart and now read this vertically. A positive second derivative means an increasing first derivative means a concave up original graph. And this, in the other side, a negative second derivative means that f prime is decreasing, means that f is concave down. And so I can see all of that stacked in my fun chart. A new piece of vocabulary is something called an inflection point. An inflection point happens if the second derivative at some value is equal to 0, or if the second derivative is undefined. And f double prime changes from positive to negative, or negative to positive. Or if my first derivative changes from increasing to decreasing, or decreasing to increasing. So this is a lot of information to kind of digest here, okay? So let's look at a graph. On this graph, this is the original function f. The original function f. It says to state the signs of f prime and f double prime on this interval from 0 to 3. So let's look at a number of things. The first thing, we want to look at slopes. Everywhere I would draw a slope on this graph appears to be negative, which would lead me to believe that the derivative is in fact negative on the interval from 0 to 3, because slopes are in fact negative. If we look at the curvature of this function, I can tell that there is a slight concave up sort of behavior here, which would lead me to believe that the second derivative is in fact positive on the interval from 0 to 3, since the concavity of the graph is concave up, okay? Let's dive deeper. If we look at a function like x to the fourth minus 4x cubed, I can now answer a ton of questions about it. I can find the intervals where it's increasing and decreasing. I can find relative extrema. I can find where f is concave up and down, and I can find the inflection points. All along, we're going to justify our answers. Okay? We're going to justify our answers. So let's start by taking a derivative. Taking the first derivative, we get x to the fourth, 4x to the third minus 12x squared. I'm going to set it equal to 0. We're going to factor out a 4x squared, leaving me with x minus 3. I'm going to get two critical numbers, x equals 0 and x equals 3. And we're going to make a number line for f prime. We're going to put 0 and we're going to put 3 on it, our two critical numbers. So we're going to test values into our derivative. I think it's easiest to test into this factored form. If I plug in a negative number like -1, I'm going to get a negative derivative. If I plug in a number like 1, I'm also going to get a negative number here. And if I plug in a number bigger than 3, like maybe 5, I end up getting a positive number, which tells me that f is going to be decreasing, decreasing, and then increasing. So I can actually go ahead and answer part A. Part A asked me to find where f is increasing and f is decreasing. So f is increasing from 3 to infinity, and f is decreasing from -infinity to 0, and then also from 0 to 3. For part B, I wanted to find the relative extrema, both relative maxes and mins. There appears to be no relative max because it doesn't go, f prime does not change from positive to negative anywhere. But there does appear to be a relative min, and that relative min is happening right here at x equals 3. So let's say 3 comma and leave it open for a second. Since f prime changes from negative to positive, make sure you specify what's changing, f prime. If I want this y value, remember, you're going to have to go plug that all the way into the original function. So plugging in 3 to a power of 4, and then minus 4 times 3 to a power of 3. Correct me if I'm wrong, but I think we should get -27, okay? So then it says we want to find the intervals where this thing is concave up and concave down. I want to find a second derivative. So we're going to take the derivative again. So we're going from here to here and we're taking another derivative. We've got 12x squared minus 24x. I want you to set it equal to 0. Let's take out a 12x, which will leave us with x minus 2, which means that we get x equals 0 and x equals 2. Now, these are not your critical numbers. These are not your critical numbers. These are numbers for concavity. So we're going to make a number line, and we're going to label that number line second derivative. We're going to put 0 and 2 on it. And we're going to plug into our second derivative. So I'm going to pick a number like -1. That's going to give me a positive number. A number like 1 should give me a negative number. And then a number like 3 should give me a positive number. So this tells me that f is going to be concave up, concave down, and concave up again. Okay? So I can answer the question for part C. Where is it concave up? it's concave up from negative infinity to 0, also from 2 to infinity. It's going to be concave down from 0 to 2, which means I can also now answer part D. Part D asked me for inflection points. Inflection points are wherever you're going to change concavity. So notice it changes concavity right here and right here. So I'm going to have a point of inflection at x equals 0 and also at 2 because the second derivative changes sign from positive to negative or negative to positive, okay? Now the last thing that this asked me to do was to make a sketch. And sometimes I think that curve sketching is really, really, really hard. So I'm going to do the best I can here, and I'll show you the way that I make sketches, and we'll just go for it, okay? So I've got 1, 2, 3, negative 1, negative 2, and obviously I'm going to have to go, we're just going to pretend this is like negative 27 down here. All right? So you're going to have to look at two things to be able to make this sketch. You need to be looking at this number line and also at this number line. And you're going to break it up into pieces. Okay? So we're going to go to 0. And if you look at it from 0, it says that the graph is going to be decreasing, but also concave up. So I need to make a graph that kind of looks decreasing, but concave up. So I'm looking at